If an object is in equilibrium, the net force is zero, so its acceleration also has to be zero. That's just Newton's first and second law. The total moment of all forces is also zero. Now in theory, this would also include objects that move, but with constant velocity. But usually we look at stationary objects, like bridges or buildings. Now let's look at stuff that moves. Kinematics is a sub-branch of dynamics. In dynamics, we take forces and their influence on the motion into account. In kinematics, however, we only look at the motion without talking about the forces. The simplest way an object could move is in one dimension. Now the following three equations are like the bread and butter of a one-dimensional motion. And if you're dealing with free fall or vertical throw problems, we just replace the a with a minus g. I can't stress this enough, because if the acceleration were positive, or the ball is thrown upwards, then the ball wouldn't eventually fall down, so don't mess it up. We talked about vertical throw, but what about horizontal throw? Horizontal throw is actually 2D motion. When we have two dimensions, we get two components to describe both dimensions. They are independent of each other, which is why we have separate equations for the x and y direction. If you throw a ball from a cliff, one perfectly horizontal and one where you just let it go, then they fall at the same rate. Now objects can also move in a circular way. When I went to the playground as a kid with some friends, there always were these mini orbiters / carousels. Let's say you and one of your friends go on one of those and spin it to achieve circular motion. The speed that you are experiencing on one of those is what we call tangential velocity, because your velocity is tangent to the path of a circle. If your speed would be constant, then we would call that uniform circular motion. Now you and your friend are finishing one revolution at the same time. However, you cover a lot more distance, which is why your tangential velocity has to be higher. There's also something called centripetal acceleration, which points towards the center and causes the circular motion. You are probably wondering why there's any acceleration, since we just said that the speed is constant. And it is, however, due to velocity being a vector and the vector changing, there must be an acceleration. We write it as the tangential velocity squared over the radius of a circle. Now since there happens to be an acceleration, then there must also be a force present, according to Newton's second law. And this is where we dive into kinetics, the branch of physics that takes forces into account. The centripetal force is just mass times the centripetal acceleration. And we already know what that is, so if we plug it in, we get mass times the tangential velocity squared over the radius. In this case, the centripetal force is the net inward force provided by the friction between your shoes and the ground, as well as you holding onto the rail. It always points towards the center of a circle. In our solar system, it would be the gravitational force that tries to pull Earth towards the sun. So let's talk about space. Besides Newton's three laws, Newton also came up with the law of universal gravitation. This guy. In it, the gravitational force is equal to the gravitational constant g times the masses of two different celestial objects, like the Earth and the Moon, over the distance of the centers of both masses squared. The reason why I said celestial objects would be that the gravitational force of smaller objects, like you and me, is completely negligible. I mean, your pencil isn't following you around because you have a bigger mass than it. The gravitational force always points towards the shared center of mass of the two objects. We call it the barycenter, and both of these two orbit around it. If you want to know the gravitational acceleration of any celestial object, you would set Newton's law of universal gravitation equal to mass times acceleration. Here capital M is the mass of a celestial object that gets orbited. Now let's talk about the most famous mechanics problem, the incline plane. Let's say we have a 10 kg box on the top of the incline plane, the angle here is 30 degrees, the coefficient of kinetic friction is 0.1 and the coefficient of static friction is 0.3. And we want to find out whether the box is going to slide down or not. Now I mentioned kinetic and static friction, but why are there two? And what is friction in general? Let's say we have a box and you try to push it. By doing so, the friction force, which points into the opposite direction you are pushing into, tries to stop you. Essentially, it's just the two surfaces bumping into each other. Every surface has its own coefficient of friction that gets influenced by the molecular structure of a given material. Now you will notice that pushing at the beginning is way harder than once the box keeps moving, which is why the static friction is usually higher. Now let's get back to the incline. The normal force points perpendicular to the surface, and Fg points along the surface. If we add this triangle here, then we will see that these two triangles are like triangles, which means that these two angles are the same. Now the weight points downward, so the hypotenuse must be the weight. This is the cosine component, and this is the sine component. The Pythagorean theorem states that a squared plus b squared is equal to c squared, and sine squared plus cosine squared is equal to 1. So we need to multiply them with the weight, because our hypotenuse is the weight. Alright, so we have a 30-degree angle and a 90-degree angle, so this triangle also needs a 60-degree angle. Notice that these two vectors are the same, and these two are equal in magnitude as well as opposite, which is why we can set them equal. If we do some math, then we get about 85 newtons for the normal force. These two are the equations for the kinetic and static friction force. If our Fg exceeds the static friction force, the box will slide down. So if we calculate the gravitational force, we get about 49 newtons, which is bigger than 25.5 newtons, so the box will slide down. I mentioned the term kinetic friction earlier, but what does kinetic even mean? Have you ever put a chicken into a pot of water, which resulted into the water splashing everywhere? What the hell, pot of water? Why did you do that? The answer is energy. You know, the thing you have after drinking too many cups of coffee in order to manage an all-nighter one day before your exam. When talking about energy, we distinguish between kinetic energy, aka energy of movement, and potential energy, stored energy that gets released due to gravity. Right before you dropped the chicken had lots of potential energy due to it being held above the ground, and after you dropped it, it converted it into kinetic energy, which resulted into the sum of kinetic and potential energy is what we call mechanical energy. If we neglect friction, then the initial mechanical energy is equal to the final mechanical energy. Because energy cannot be created nor destroyed, only converted. That's what we call the conservation of energy. Now energy has the unit joule, just as work. But what's work? Work is defined as force times distance. If you push a box horizontally with a force of 1 Newton 1 meter away, then this means that you did about 1 joule of work. If you apply a force at an angle, we would add a cosine. Energy and work have the same unit joule, so are they the same? No. Energy describes the ability to do work. It's a property of an object or a system, while work describes energy being transferred from one system to another via a force. Do you remember those spring jumping sticks from the late 2000s? Those have a spring in them. In physics, there's something we call Hooke's law. It says that the force of a spring is equal to minus kx. Why the minus sign? It's because if you pull the spring, you will feel a resistance which points towards the opposite direction you are pulling the spring from. The k stands for the spring constant. The higher k is, the greater the force would be that the spring can exert. And the x just stands for the displacement of the object attached to the string. If we take a look at our bouncing stick, then we have to rewrite Hooke's law, with x0 being the mass of the thing attached to the string times g over the spring constant. x0 is the new equilibrium position. The spring is going to oscillate around it before ultimately settling there. Now let's say you were jumping with a toy stick around the neighborhood but didn't check your surroundings, which is why a truck crashed into you. That's what we call a collision. There are two types of collisions: elastic collisions, with the momentum being mass times velocity, and inelastic collisions. In an elastic collision, momentum and total kinetic energy are conserved. So if two objects collide, then they perfectly bounce off of each other without losing energy. In an inelastic collision, only the momentum is conserved. This means that if we have two objects that collide, some of the energy turns into other forms like heat, deformation, and noise. In a perfectly inelastic one, they would also stick to each other after the collision. Have you ever seen a door? If so, then you probably noticed that the doorknobs are far away from the hinge. But why is that the case? The answer is torque, which is equal to force times distance times sine theta. You see, the higher the distance from the axis of rotation is, the higher the torque. That's also why longer wrenches are usually more effective. F is the force you apply, but why is a sign there? Well, it just tells you that if you apply the force perpendicular, then the torque is higher than if you would apply it at an angle. Do you still remember the linear equations we used earlier? Well, it turns out that if you modify them, then we can use them for rotational motion. The angular velocity is d theta over dt, and angular acceleration is just the derivative of it with respect to time. Both of them use radians. You can also use radians for the torque equation from earlier. But what are radians? The circumference of a circle is 2 pi times the radius. Radians just tell you how much of that circumference is covered by the given angle. These two are the conversion formulas. But what is 1 radian? If you have a circle with an arc that has the length of a radius, then you get 1 radian. Now we know that the circumference of a circle is 2 pi r, and since one arc length is r, we need 2 pi radians to cover the circle, which is about 6 arc lengths plus about 0.28. If we set 2 pi radians equal to 360 degrees, then you get that 1 radian is about 57.2958 degrees.